Today we're going to expand on zeros of polynomial functions by looking at all of the possible rational zeros for a polynomial function. In doing this, then we will determine what are the actual zeros for the function, and then we can discuss things about what are the positive real roots, negative real roots, and if we have complex roots as well. So how do we go about determining what are possible rational zeros? Well, you'll notice we have this equation down here, and it says we need to take the factors of p, which is the constant right here, and divide them by the factors of q, which is the leading coefficient. So again, if the polynomial is of the form, and they put, instead of a sub n, they put q, x to the n, plus a sub n minus 1, x to the n minus 1, plus dot, dot, dot. Right, we're just saying that basically the a sub n term we're now calling q, and the a sub 0 term we're now calling p, if you recall the previous definition we had for a polynomial. So factors of the constant divided by the factors of the leading coefficient. Things that we'll use a little bit later are these properties here for the roots. The first states that if we have a degree n, remember that the highest power on the variable gives us the degree, then if we consider multiplicity for roots as being separate solutions, the equation has exactly n roots. So for instance, if it was x to the 5th power, that has 5 roots. They could all be 0, right? It could be 0 with multiplicity 5, but there's 5 roots. Additionally, if we end up with a complex solution, for instance, a plus bi, again, b cannot be 0, making it a complex root, then the imaginary number a minus bi is also a solution. And this is because the imaginary roots must exist as conjugate pairs. So if you get one solution, then you better get the other one. So let's take a look at this first example and see if we can't figure out all of the possible rational zeros for this polynomial. So again, we need to figure out what is p, what is q, and while we're at it, let's talk about n. So what's the degree of this polynomial? Well, the highest power on a variable is 3. So this is degree 3, which means this function has 3 zeros. That tells us that basically if at this point, right, we get less than 3 possibilities, well, then we did something wrong. So p, right, is the constant. That's 4 in this case. And that has factors of 1 and 4 and 2 and 2. And in fact, it also has -1 and -4 and -2 and -2, right? If we multiply two negatives, we get back a positive. Q, on the other hand, is the leading coefficient. This is Q right here. Q is 5. Well, that has a lot less factors. It has 1 and 5 and -1 and -5. Now, the formula said to take all of the possibilities for P and divide them by all the possibilities for Q. So technically, what I need to do is take every one of the factors of P. So I would do 1 divided by 1. Then I would do 1 divided by -1. Then I would do 1 divided by 5 and 1 divided by -5. That's all just for P equal 1 and all possibilities for Q. Instead of writing them out all like that, let's do it a little differently. Let's instead say, okay, this is the possibility of having plus and minus 1, plus and minus 2, and plus and minus 4. Those are all of the possible factors. And for Q, we have plus and minus 1 and plus and minus 5. Now, we can write this much nicer if we do P divided by Q, right? We could do plus and minus 1, plus and minus 2, plus and minus 4, all divided by one of the options for Q, which would be plus and minus 1. Or we can do all of P divided by another Q. Okay? Now, if we look at each one of these separately, right, we're going to get plus and minus divided by plus and minus, by the way, just returns plus and minus. So we get plus and minus 1 divided by 1. That's plus and minus 1. 2 divided by 1. So we get back 2. And then 4 divided by 1. So we get plus and minus 4. Over here, we get 1 divided by 5, plus and minus 1/5. 2 divided by 5, or 4 divided by 5. These now are all of the possibilities for roots. We know for a fact that only 3 of them can be true, right? At most 3. It could be as little as one of them repeated 3 times. Okay? All right, let's take a look at another example. So here, just be careful. Notice that the leading coefficient here is actually -9, right? Just because it's written second doesn't mean it's the leading coefficient. So maybe you might want to rewrite this first, putting it in descending order. Okay, so this is our P. I'm sorry, that's our Q. That's our Q. It's the leading coefficient, and then P is the constant. So what are factors of P? And actually, before we do that, what's N, right? What is the degree? It's degree 4. So there should be at least 4 solutions. Okay. P is 6. What are factors of 6? Well, we could have 1 and 6. And we can have 2 times 3. Okay. So that's 4 possible factors, right? 1 and 6, 2 and 3. And then, of course, the positives and negatives also, right? If we had -1, -3, so on. I'm sorry, -1 and -6. What about Q? Well, Q is -9. So how do we get -9? Okay, so here we get 1 and 9. We can have 3 and 3. Now, of course, we need specific combinations of those, right? -3 and +3, -1 and +9, +1, -9. But they still require positive and negative as a factor. So we have all these possibilities now. So I need to take each one of them and divide, or each one of the P's and divide by each one of the Q's. So for P divided by Q, I have plus and minus 1 over plus and minus 1. And I'm just going to write them out from here on, right? Not necessarily saying each one as I go. And what you'll notice here in a second, as soon as I get on a little bit of a groove here and get moving a little faster, is we're going to get some repeats. So let's see, plus and minus 3 over plus and minus 9, okay. Just need to get 6 out of the way. Okay, so the first option gives us 1, right? Plus and minus 1. Is there any other case where we see that? Well, we have plus and minus 3 over plus and minus 3, right? So that's a repeat. The second option is plus and minus 1 over plus or minus 3. So that's 1/3. Do we repeat that anywhere? Well, we have 3 over 9. If we divide both of those by 3, you get 1/3. So that's a repeat. All right, then we have plus and minus 1/9. 2 over 1, so plus or minus 2. Then we actually have 2/3. I think I'm going to need to scoot this over so I have enough room. All right. Then plus and minus 2/9. Then we have 3 over 1. So that's just 3. 6 over 1. 6 over 3, well, that's just 2. We've already got 2, so that's a repeat. And then 6 over 9 is going to reduce down to 2/3, which we also already have, so that's a repeat. So these are all of our possibilities, of which we require 4 roots. Again, remember, it could be as little as one of them. That's repeated 4 times, or we could have 4 separate roots. And in the next videos, we're going to learn how to actually determine whether one of those is an actual 0.